The next example I want to go over is the structure factor of the rock salt or sodium chloride structure. So we're not necessarily talking just about sodium chloride, but we're talking about the structure. So I've drawn the structure here. It will also be in the quiz. And before we get to the structure factor part of this, for the quiz question, what I want you to do is, for the structure factor, we need to know what the fractional coordinates will be for the sodium and for the chlorine ions in the unit cell. So take a look at the structure and see if you can write out the fractional coordinates for the sodium and for the chlorine ions in this structure. And take note of how many of each there are, how many ions there are per lattice, and that will help you determine how many you need for the structure factor calculations. So do that, I'll come back and we'll work this out, and then we'll go ahead and do the structure factor calculation. All right, so for the sodium chloride structure, for my drawing here, the black ones on the corner and the face-centered positions are sodium chloride, and the ones on the centers of the edge and the middle are chlorine. So if you work out the numbers here, if sodium is on the corners and in the face-centered positions, then there should be 4 Na plus per unit cell. So we'll need to know 4 positions. And for the chlorine, if you do the same count, you'll find that that's the same as well. And since it is a structure where we have 1 cation, 1 anion, so 1, 1 stoichiometry, then this should also be the same. So we should have equal numbers of the positive and the negative ions per unit cell. So they should equal each other. So we're going to have to find the positions for 4 of the sodium and 4 of the chlorine. All right, so those positions, so let's start with sodium. Like I mentioned, you can think of these as the FCC positions in this structure here, if you kind of look at where all the black ions are. And so that means that it's going to be on all of the primitive sites. So we'll represent that as 0, 0, 0. But then there's also going to be 3 FCC types in those cases. So if we look at the position here, this is 1/2 X, 1/2 Z. So that would be 1/2, 0, 1/2. The one down here would be 1/2, 1/2. So 1/2, 1/2, 0. And then you can pick another one, and so we could pick the back corner, and so that would be 1/2 in the Y, 0 in the X, 1/2. So 0, 1/2, 1/2. So I've basically picked primitive, which is 1 atom per unit cell, and then 3 face-centered because we have 4. So that gets us to our total number. So again, obviously, you can locate more than 3 face-centered positions, but they're sharing, so we only need to identify 3 to describe the whole structure. Chlorine, same thing, we need to know 4. So we need to know 4 positions for the chlorine. And so we can go in the same direction. So they are on the center of the edges here, like here, here, and here. And then also you'll see, it's a little hard maybe to see in my drawing here, but there's also one right in the center of the unit cell. So we know that the center of the unit cell is the body centered, and that's 1/2, 1/2, 1/2. And also if they're on the centers of these edges, that is of the type 1/2, 0, 0. So I've got 1/2, 0, 0. There's also one over here, so 0, 1/2, 0, and then also 0, 0, 1/2. So that would describe all the positions. Again, even though there are more of these edges, they're sharing, so we only need to identify 3 of them. So that's what I was looking for in terms of the positions, because we're going to need to know these for the U, V, W values of the various ions in the structure to be able to do the structure factor calculation. So let's go ahead and take a look at that. Okay, now that we've got the UVW for all of our ion positions, now we're going to start plugging in to the equation. So if you forgot, here's our structure factor calculation. And so we're going to leave for now, since we're not worried about a particular plane of HKL values, we're going to leave that as HKL. And then we're just going to plug in these UVWs for the various ions in the structure. And then we'll see if we can simplify it at all. Okay, so starting with the sodium positions, let's go ahead and write this out. So I've got F, and here I have the atomic scattering factor for sodium. So I'm going to specify the ion I have. Again, if you're not looking at the sodium chloride structure, this would just go to the cation. And then I have the exponential, and here I'll write it as exponential to the power. So that will be 2 pi I as always, and then it'll be H KL multiplied by the values of this, the dot product of those two. So the first position I have is 0, 0, 0. So the 0, 0, 0, the 0 times this, 0 times that, 0 times this, of the HKL values is just going to be 0. So we've got 0 here for the first term. So basically, anytime you have the primitive case, that's always going to end up with 0. Second position, now I'll move on to this one, is going to be, again, sodium, 2 pi, exponential of 2 pi I. And then in this case, I'll have this multiplied by H. So I'll have H over 2. And then this will be a 0, and then it'll be plus L over 2. So I'm just kind of doing a couple steps in there of the basic algebra. So then if I move on to this one, the next one here, it'll be H over 2 plus K over 2, and then the L term will be 0. And then I've got one more term. And in this one, it's going to be K over 2 plus L over 2, because I have the 0 here. So I'm multiplying the U term by H, the V term by K, and the W term by L, and that's where I'm getting these values, and I'm adding those together. So there's 4 terms for the sodium, and now I'm going to look at the chlorine terms. So I'm switching over to that, and again, if it's not specifically sodium and chlorine, but just has the structure, then you would switch out whatever those specific cations, anions are. So for chlorine, the first term, we're going to go with the body center position. And so this is going to be H over 2 plus K over 2 plus L over 2 for the body-centered position. The second term, they all have a very similar format to begin with, but then we have 1/2 0, 0, so that's going to be H over 2, and then everything else is going to be 0. Plus, and you can see where this is going, there's going to be H over 2, K over 2, and L over 2 for the last terms. So I'll just go ahead and write those out. Okay, so that's kind of written all out of plugging in our UVWs and multiplying them by the general HKl terms. So now what we want to do is see if we can simplify this expression. So we know that this first term is going to go to 1. We can take the 2 out and remove this 2. So let's go ahead and write that. So we've got F sub Na, and then it's going to be multiplied by 1 for the first term, plus E, and then the 2 and the 1/2 are factoring out. So I got pi I times H plus K. And I've kind of rearranged them here, but I'm going to have this, and then I'm going to have the H and L term. So I just rearranged them, but it doesn't, so essentially this term I factored out from here, this term I factored out from here, and then the same thing I'm going to have on the last one, K plus L. So just slightly rearranged it, but really the same thing. And then plus the chlorine terms. Here I can again factor out the 1/2 and take out the 2. So this is going to be H plus K plus L. Plus, and then again the 1/2s all factor out. I've got pi I times each of the terms. Like that. Okay, at this point we've got it to a certain level of simplification, and there's actually a couple more that we can do. And the first part of that is to go back and look at the structure itself. So we talked about the sodium chloride, or sorry, the sodium positions being in FCC, right? So if you exclude the chlorine, the sodium looks like FCC. Well, the chlorine is the same. It has 4 chlorines per unit cell, and it's in fact in an FCC arrangement. It's just offset by a certain translation, right? So effectively, we can make the chlorine, if you sort of keep drawing it. For example, so these are chlorine here, 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 and there would be one in the mid position here and here, right? And so that forms the sort of the basis of an FCC 001 plane. So chlorine is also in an FCC arrangement. It's just offset by one of those translation vectors, right? And so we can offset that basically. For example, if we shift the chlorine position over by 0, 1/2, 0. That's a translation vector for those two. And so we can basically use that knowledge, use that face-centered translation, and basically apply the structure factor calculation that we would get from an FCC arrangement. So we haven't gone over that, but you kind of see what it looks like here. And so we can do that, and effectively that's going to factor out. And so we can redraw that, or we can rewrite this, and let me go ahead and do that for you. And I'll put this up here. So we can now write this as, so basically everything will stay the same for sodium. So that's the same, but our chlorine is going to factor out. And in this case, what they're using for the translation here is the 1/2, 1/2, 1/2, because we have if we go back up here, we have a body-centered position. So they're actually using that translation instead of one of these. And so if I do that, and I use that as my common factor, then I will get if I factor that out, my expression will look like this. So I've basically factored out this from the previous expression to get what I have here. And so another kind of tool to change the second part, the second bracket here, is to realize that if I have an exponential of nxi, it's the same as the exponential of minus nxi. They're equal for any integer n. N is that integer. So basically, we can factor that out, and that basically means that these terms are the same as these terms. And what that does is it can now be all put together like we have here. So basically, this is the expression we see in FCC, and then since we have two, what we sometimes call as sublattices, because we have this and this with the common translation vector, then our that is basically showing the two different sublattices we have with the translation vector up here. So we have FCC, and we can modify it with this term here. And again, that's because we have FCC sodium, so the Na plus ions are at 0, 0, 0, right, for FCC, and then we shift it and have a translation vector of chlorine ion at 1/2, 1/2, 1/2. Sorry. So that's where we're getting this term over here. So if we look back at the extinction rules for FCC, which again is related to this term, what we find is that the extinction rules for FCC are that the structure factor is equal to 0, so it's extinct for mixed indices. And so if you kind of look at this expression, you can hopefully prove that to yourself, that you'll get 0 if you have either a mix of odds and evens in those cases. So you might do that in addition. So this rule also applies to sodium chloride. So for sodium chloride, we also have this term is the same. But we're going to have some additional constraints as well. So additionally, and let me start on a new piece of paper here. Additionally, for unmixed, so in this case, for unmixed, we can simplify our expression to be what we see here. So let's look at the case of unmixed. So in FCC, we saw that we have peaks when they're unmixed. So let's look at the examples of if they're all even or all odd. So for even, then we would get this. And again, if you want to plug in all the numbers, I recommend you do that. But this is the expression if we have H plus K plus L is even. And we'll often see this term squared. So I'll just go ahead and write that out. So for some additional calculations later, you might use this F squared version. And then if we have the sum is odd, then we'll have this form of the expression. So this is kind of what separates sodium chloride from FCC, is that for those unmixed indices, in FCC they're all the same, but here we can see that the intensity based on the structure factor is actually going to be different. For when it's even, you have these added together, and then you have the subtraction when it's odd. And so that's kind of the distinction here, and separates sodium chloride from FCC. And so again, the squared version of this I'll write out real quick, and that's what you get. So again, the reason we talked about Bravais lattices was to kind of make the realization that this rock salt structure has an FCC Bravais lattice, but it also has 8 ions per unit cell as opposed to 4, and so we can relate it to a FCC Bravais lattice in the structure factor calculations, and then just act like it has multiple ions per lattice point, right? So effectively, there's 2 ions, a sodium and a chlorine ion per FCC lattice point. So that's the idea here. And that means that we have the same reflections, but there's some differences in the intensity here in those cases. All right. One last thing I want to mention about these structure factor calculations is, as you're going through this, one thing that you'll hopefully note is that nowhere was there anything about the unit cell shape, right? So the fact that it was cubic or hexagonal or so forth didn't come into these equations. Also, the size, the relative size, right? So if you're looking at, for example, 2 FCC metals, they're going to have different lattice sizes. The unit cell is going to be different volume and so forth. Nowhere in this did that come up, right? So these equations, the structure factor is independent of the shape and size of the unit cell, right? It only cares about where the atoms are located, etc., to do those calculations. So that's the kind of key here when we're talking about it. It's independent of shape and size of the unit cell.